Section 3.6, we're going to talk today about curve sketching. As a way of checking, you are welcome to use a calculator to check what you're going to do on these problems. I would expect that you should. However, I will say that without the proper justification, a graph with no justification is going to get like 0 points, okay? So the kind of justification as we talk through this is going to be expected to be seen on every problem, and that's why we're going to do some work on the boards when we're at the end of class today. Sound good? I'm going to take that as yes. Okay, important graphical features. There are 3 categories of features that your book outlines as being important graphical features. The first one they talk about is domain and range. This is valuable. It's valuable more so in some cases than others. In particular, the domain and range come into play a lot with rational functions and radical functions, which is the 2 examples I'm going to show you today. But honestly, the asymptote feature in number 2 is going to play a lot with that domain and range piece for rational functions. And then we're going to have radical functions, which are a little bit different. The one piece, intercepts, that's where it crosses the x and the y axis. So remember, domain is the x values that are allowed. The range is the y values that are allowed. A lot of times it's easier to look at what's not allowed and sort of phrase it the opposite way. And then symmetry. Symmetry doesn't happen in a lot of graphs, but when it does happen, it is quite useful. So you might imagine something like a graph of y equal x squared, right, where it's symmetric around the x-axis, or excuse me, around the y-axis, something like that. So sometimes that's a helpful feature. And then the last one right there that you'll see, it says to locate the values where f prime of x and f double prime of x, it's not kind of hard to see if that's a double prime, but are either 0 or do not exist. So what you're kind of looking for when you're doing step 3 is things where when your first derivative, when you consider your first derivative, maybe we should ask that as a question to you. What kinds of information does your first derivative tell you about a graph? The slope of the graph, right? So what does it tell you about the graph itself in terms of how it's shaped? What features about the graph does it give you information about? There's 3 features it tells you about. I guess you could maybe classify it as 2. One is increasing and decreasing, right? That's what the slope tells you, is whether something's increasing or decreasing. So the slope graph, the f prime, is going to tell us information about where it's increasing, where it's decreasing. It also tells you one more thing. Yeah, the critical points, potentially at least, are what? What could those be? So the slope is 0, right? But what is it? What kind of picture do you get when the slope is 0, potentially? What's that? Well, usually we call them relative extrema. Remember that word? I know that was way back in 3.1. That's been like 3 weeks at this point, maybe 4 because we had spring break in there. But it's been a while. So relative extrema, it tells us points where it has peaks and valleys. That's sort of a non-math term for it, but peaks and valleys. What does the second derivative tell us? That's been much more recent. Yep, concave down and concave up, right? And then at the place where it changes concavity, what do we call that? An inflection, or a point of inflection, or an inflection point, exactly. All right, so those kinds of pieces of information give us features about the graph. If a graph is increasing and concave up, it looks different than if it's increasing and concave down, for example. Okay, so we're going to use these pieces of information to analyze and sketch a graph of a function. On the graph, we're going to label any intercepts, extrema, points of inflection, asymptotes. Okay? So we're going to go through basically these 3 steps, and all the features that are listed here, we're going to write down what they are. That's the justification for the graph that we're about to draw. We're going to find the domain, the range, the intercepts, all the way down the list. Okay? So let's start with this graph in terms of domain. What issues, if any, are we going to have with the domain for this function? Right. X cannot equal 0. In fact, what would happen if x did equal 0? What happens? It's an undefined because there's an asymptote. So here in a minute, we're going to write down that we have an asymptote there, or you can write it here. I'll just skip a space so I can write range in. We know that we have an asymptote when x does equal 0. Okay? I mean, those 2 things are really like the same piece of information, or at least almost. Range, we skipped range, so let's go back and grab range. Range is y values. Now, this isn't exactly something we have talked about these, but does anybody remember what happens when you're dealing with range and rational functions? Rational functions might have horizontal asymptotes, right? Right, it plays horizontally. Like if you consider the graph, just a typical graph of y equal 1 over x. The graph of this looks something like this, and it has this horizontal asymptote along the x-axis, along the line y equals 0. That has a potential for happening when you have rational functions. So let me remind you, and jot them down if you don't remember them. There are 3 possibilities when you're dealing with rational functions. One possibility is that the degree of the numerator is less than the degree of the denominator. That's this one. Degree means the highest exponent. The highest exponent of the numerator is 1. The highest exponent of the denominator is 3. If the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote at y equals 0. Okay, that is what's happening on this graph. So we have an asymptote here at y equals 0. It also means then that the range is such that y does not equal 0. That doesn't always happen with horizontal asymptotes. It does many times on this one, and that's not even quite true. We can get this one to be equal to 0. I'll show you. I wrote this down wrong. Let me go back to that one in a second. Okay, let me tell you the other 2 cases for horizontal asymptotes. The second case is the degree of the numerator is bigger than the degree of the denominator. So like if we took this fraction and the fraction were inverted, right, the reciprocal of it, so that the x cubed was on top and the x was on bottom, then it would not have a horizontal asymptote. Okay? That's a distinct possibility. All right, the third possibility is that the degrees are the same. Like let's say, for instance, this said x cubed minus 4 over x cubed, right? Both of them have powers of 3. In that case, you take the coefficient in front of the highest degree term from each the top and the bottom, and that would be your example. So like if you had, oops, this, degrees are the same, so the horizontal asymptote is y equals 3/4. Okay, so it's a brief reminder of asymptotes. It's a college algebra, algebra 2 concept. For us, we have the case where the degree is on top is less, so we get y equals 0. I'm going to come back to the range because let's do x-intercepts, y-intercepts next, because that will affect our range. How do I find an x-intercept? Algebra topic. How do I find an x-intercept? What can you tell me about that point? Y is 0, yeah. So the x-intercept is when y equals 0. Okay? So if I were to try to let y equal 0, that would mean that I would need this to happen. Right? Well, what value would make this whole fraction equal to 0? 4. It's where the numerator equals 0, right? If the x value in the numerator were 4, I'd get a 0 in the numerator, which would make the whole thing equal to 0. Denominator is not 0, so that's okay. So this would happen at x equal 4. So the x-intercept is actually 4, 0. I'm going to pause right there to make a mention of the fact that this feels a little bit funny, because we said that we have a horizontal asymptote at y equals 0, but we're also clearly crossing the line y equals 0 at x equal 4. Those 2 things are not mutually exclusive. You don't have them happen very frequently, but they can happen. So because that's happening, my range is actually all real numbers. There aren't any values in my range that I can't have, because I actually just showed that the one value that might happen, the horizontal asymptote, doesn't. I have an intercept there. So the graph will have an interesting feature because of that. We need to do the y-intercept. How do I find the y-intercept? What do I do? Yeah, I let x equal 0. What happens on this one if I do that, if I try to do that? Yeah, so I try to let x equal 0, but that does not work, right? Because that is not defined. I get a 0 in the denominator because there's an asymptote there. So there is no, or none, I don't know how you want to write it, there isn't one. We don't have a y-intercept. It will not cross the y-axis. Yeah, you can say does not exist. That would be perfectly fine. All right, so I think, let's see, what else have we gotten? Symmetry. There's no symmetry on this. In order to have symmetry, we're going to have, well, that -4 there throws things off. Once I have that -4, I'm not going to have the symmetry. You're usually looking for powers that are even to make the graph even, right? The reflection on the left and right, like the line or like the curve y equal x squared. Or if you had cubes, you would have a reflection that's odd, which means you could rotate it 180 degrees potentially and have the same thing. The reason this one won't have that is because the -4 on top doesn't have an even or an odd feature. So there isn't any symmetry. There's not symmetry a lot of the time. You'll know it when there is because you see it very easily. So when you don't see the symmetry, it's typically speaking not there. Okay? It's really not that useful of a feature in graphing anyway. The next pieces then are talking about the derivative. So I need you guys to find, or help me find, the derivative of our function. So walk me through it. What do we get? You can if you'd like, or we can use the quotient rule. I think the quotient rule is probably just as clean because we're going to take a second derivative here later anyway. And it's usually easier to use the second derivative from the quotient rule. So I think we start with x cubed, right? Times the derivative of the top, which would be 1, minus the top, which is x minus 4, times the derivative of the bottom, which is 3x squared, all over x cubed. All right, I'd like for you to clean that up for me really quick, and I'd like to know what the final, what did I do? Oh, yes, a 6th here, thank you. I'd like to know what the final simplified version of this looks like. If somebody, when you get to that point, let me know. Is that what your next step looked like? Yeah? So you have x negative 2x cubed plus 12x squared, and then what do you think you can do? Yeah, everything has a power of 2 on the x, right? So if I divide everything by x squared, I get negative 2x plus 12 over x to the 4th. The goal in having this is to set this equal to 0 and figure out, using this information, what the first derivative tells us. And we said when we first started this process, it's going to tell us where it's increasing, decreasing, and relative max, relative min. That's what we're looking for. So where does this equal 0? Yeah, at x equals 6. So, sorry, I'm trying to consolidate this onto one screen. Let me try again. All right, so there's all of our work. We're going to make a number line. The number line will include what? 6. It actually needs to include something else as well. 0. Why does it need to include 0, Nate? Because why? Yeah, it does not exist at 0, right? So we need to include the does not exist points as well. So like, where does this does not exist? It does not exist at x equals 0. All right, so we need to test a point in each of these intervals. So maybe we test -1, 1, and 7. And we test it into which graph? Or which equation? The derivative. The derivative tells us information about increasing, decreasing, max, min. So let's plug these in. Do I care about the sign or do I care about the actual value? Just the sign, because the actual values that I'm plugging in I made up anyway. It's the sign I care about. So what happens when you plug in -1? A positive? What happens when you plug in 1? A positive? And 7? Negative. So let's write down some of the information. I can tell from this, and I know you can too, where is this increasing? Okay, negative infinity to 0, and then 0 to 6, because remember there's an asymptote in between there. And then I've got decreasing. Where is this decreasing? Well, 6 to infinity, right? Increasing, decreasing information. How about max min? What does this sign chart tell me about maximum and minimum values? Well, what does positive mean? We said it means increasing, so it's going up right here, right? And then this is positive, so it's still going up on this piece of the graph. And then what happens on the next piece? It's going down. So this location changed between increasing and decreasing. So is it a maximum or a minimum? It's a maximum, right? It went up and now it's going down. This is a relative maximum. So we have a relative max. And the value is at x equals 6, but it would be helpful because we're going to be graphing this to find out what the y value is. How would I find the y value that goes with x equals 6? Plug it into the original. And an approximation would be just fine here. So if you plug that into the original, what's the decimal approximation you get? Yeah. Awfully close to the x-axis, but it is 0.009. All right, so I'm supposed to find the, using this, I'm then supposed to find the second derivative, right? So my first derivative, I'll move to the other slide. Is this one. What is my second derivative then? Okay, well I'm going to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So what's the denominator going to be? Don't everybody answer all at once. X to the 8th. And we clean up the numerator, right? That's an 8. Doesn't look very good. That's better. All right, so I have negative 2x to the 4th. This would be plus 8x to the 4th. And then minus 48x cubed all over x to the 8th. Part of that numerator combines, so then I have 6x to the 4th minus 48x cubed over x to the 8th. Then what? The x's. There's powers of x's and everything, right? Highest, or the lowest power, excuse me, is x cubed, so we can take an x cubed out of everything. So this would then be 6x minus 48 over x to the 5th. Why did I find the second derivative? What's the point? Concavity. It's about concavity, so what do I do next in finding concavity? Set it equal to 0. And that will find us possible inflection points. So where will this equal 0? At x equal 8. And we also look at where it doesn't exist, and where does it not exist? Yeah, at 0. So those are the 2 points on our sign chart that we need to have included, 0 and 8. And we'll test a point in each interval. So a little bit ago we used -1 and 1. Those are still good points to use. And then we need something bigger than 8, so maybe we pick, I don't know, 10 or 9 or something like that. So then, plugging in -1, I need to know, do I get a positive or a negative? Where am I plugging it into? Second derivative, yeah. So plugging these values into the second derivative, that's 6x minus 48 over x to the 5th. Positive or negative on -1? Positive's right. How about on +1? And on 10? All right. What do the positives tell us? Yeah, so it's concave up on -infinity to 0 and 8 to infinity. And it's concave down on 0 to 8. And it also tells us that we have a point of inflection, we'll do POI, where? Where do we have a point of inflection? It is. Why do I not have a point of inflection at 0? There's an asymptote actually at 0. So you have to remember what those values came from. The x equals 0 is actually an asymptote. But I do have x equal 8 as a legitimate point of inflection. And then how do I find the corresponding output value for that? And what do you get? Plug it into the original, what do you get? Should be quite small. It was already quite small at, what do we have before 6? 0.0, like this? Okay, can I do it look like that? I mean, I'm going to be graphing it. I'm not going to be able to graph it any more specific anyway, correct? So it should be okay. All right, let's take a look at the graph. So we've got our xy axis. We need to have the features on the graph that are included on this list of features, basically. So we're supposed to have an intercept at 4, 0. So here's my intercept at 4, 0. We're supposed to have an asymptote at y equals 0. And then also, sorry, that was my x equals 0. Also one at x equals 0. So x equals 0 and y equals 0 both have asymptotes. If I move from the left-hand side to the right-hand side of the graph, it looks like from the first derivative it tells me it's increasing until I get to the asymptote at 0. And from the second derivative it tells me it's concave up. So I mean there's only two options here. Either the graph is here or the graph is here. I mean it has to be in one of those two sort of areas. Can't cross the axis because we didn't get any intercepts over there. So is it in the top corner or is it in the bottom corner? It's in the top corner because it needs to be both increasing, which this is, and concave up, which this is. I was supposed to have a maximum value at x equals 8, and something happened at 6, I'm sorry, at x equals 6, I have a maximum value, and it looks something like 0.09 is what it said, right? So it's barely above, I should use blue, I already did a minute ago, barely above, but it's right here. Okay, if you want to be exaggerated on it just so that you can see it a little bit better, you can make it a little higher, it's not going to hurt anything. But there's my x equals 6, and over at x equal 8, I don't have that marked out here yet, I have an inflection point. Are we sure that the x value at 8 gave us the 0.078? Because it seems like it should be lower than that.
0.0078.
I got a 0 off. I'm with you. So it's slightly less, 0078 or 008 if you round, slightly less than the value at the peak. Something like this, right? These are the points I have so far. All right, so it tells me then that between, according to the first derivative over here, Between 0 and 6, where I hit that maximum, it's supposed to be increasing. And it also tells us that between that same 0 and 6, because it's from 0 all the way to 8, it needs to be concave down. So if it's increasing and it's concave down, it would look something like this. Agreed? And then after that point, it's supposed to be decreasing from here on out. But it's decreasing and concave down until I get to my next blue dot, and then it will be decreasing and concave up, which means that it changes sort of directions like this. And it levels out there for two reasons. One, there's an asymptote, right? And two, it never said there's any more x-intercept, so I can't cross it even if I wanted to, not crossing that asymptote. So this is what we have for our graph. All right, the next graph's actually a little bit quicker to do, so let's take a look at it really quickly. F of x equals the square root of 2x minus 1. Same ideas as before, domain, range, intercepts, and so forth. So what is my domain, or what kind of issues potentially could I have when I have a square root graph? What's that? Negative numbers. And not just negative numbers, but negative numbers in certain places. For instance, no negative numbers underneath a radical, right? And I don't mean like no negative numbers. I mean whatever the resulting value is cannot be a negative number. In other words, this 2x minus 1 has to be what? Well, it has to be greater than or equal to 0, right? And then if I solve this, then my x would be greater than or equal to 1/2. So my domain, and it does include 0. Square root of 0 is 0. That's okay. All right, so my domain is actually all the x values that are bigger than 1/2 or equal to 1/2. How about range? What kind of y values do we get when we take square roots? What kind of values do we get when we take square roots? Positive or 0, right? Square root of 0 is 0. That's okay. Square root of anything else is a positive number. So the range is that y is greater than or equal to 0 because it's a square root. Y is equal to the square root of something, so it's greater than or equal to 0. Asymptotes. Well, this isn't a rational function, so there aren't any. Okay? If there aren't any asymptotes and you just leave off the asymptote part, that's okay. I'll assume that that's what you're intending. But there aren't any asymptotes. There isn't any symmetry either. We could write down symmetry equals none. Intercepts was also in there. I think I skipped over that and did those in the opposite order. Intercepts. How do I find the x-intercept? We set y equal to 0. So can y equal 0? Can I let 0 equal the square root of 2x minus 1? Sure. What would x have to equal to make that happen? 1/2. Right? Square both sides, add the 1, divide by 2. X equal 1/2. So I have an x-intercept at x equals 0. Whoops, not 0. X equals 1/2 and then comma 0. So this is my x-intercept. How about my y-intercept? Yeah, this one doesn't exist, right? We're working in the real number plane, and so we're not working with a complex number plane in calculus. There is complex number calculus. You're welcome to take it in grad school. I would encourage you to do so. Lots of fun. Fun in store ahead. All right, so no y-intercept in the real number system. Now we have information to do with derivatives. So these derivatives are actually very friendly on this particular graph. If you think about this one as 2x minus 1 to the 1/2, probably be a little easier to do the derivative for that. So what's the derivative of 2x minus 1 to the 1/2? Got a 1/2 first, right? Going to pull the 1/2 down, then what? Rewrite the original to the power negative 1/2. And then what? Derivative of the inside. So what's the derivative of 2x minus 1? 2. And as you look at the reducing, this 1/2 and this 2 are very friendly multiplicative inverses. So we're actually left with, if we turn it back into a radical function, 1 over the square root of 2x minus 1. Agreed? Okay. And the goal is to figure out where does this equal 0, and what do you find? It doesn't. This never happens. However, we can find out, hang on, this doesn't exist. Where does this graph not exist, though? How to do with the domain? Yeah, anything less than 1/2 doesn't work, right? So this is actually, the key point here, the critical point that we're caring about is the 1/2 part of it, because this graph also does not exist at 1/2 or anything less. So the reason I mention it in that way is because we need a sign chart. It's not a very exciting sign chart. It has one number on it, 1/2, and things do not exist over here, so we're not testing anything on the left-hand side. It won't work. But we still will test something on the right-hand side to see if we have an increasing or decreasing function. So maybe you like the number 1. Maybe you don't, I don't know. You can not like it, it would be okay. Do we get a positive? We do. So this graph is what? Increasing or decreasing? It is increasing. Where? From 1/2 to infinity, this graph is increasing. Fantastic. Let's do a second derivative. So again, it would probably be easiest to look at this version of the equation to do the second derivative. So I'll bring my negative 1/2 down. I'll rewrite 2x minus 1. What's my new exponent? Good, negative 3/2, and the derivative of the inside is 2. So my 2 and my negative 1/2 cancel out, leaving me with a negative anyway. And in the denominator, I have the square root of 2x minus 1 to the third. This still never equals 0, right? And it still does not exist for anything less than anything less than 1/2. So in terms of a sign chart, the sign chart looks just like the sign chart of the other one. It's D and E over here. We can test the value of 1. When I plug in the number 1, do I get a positive or a negative? Into the derivative. When I plug in the number 1, what do I get? It is negative. What does that tell me?
Concavity down.
Yeah, it's concavity down or concave down. So this is concave down on what interval? Yeah, from 1/2 to infinity. So this isn't sort of a lot of information to go on, but it's enough. What I know on my graph is that I don't have anything on the left-hand side of the graph. In fact, I don't have anything at all until I get to 1/2. So we'll call this 1, so then the number the hash mark before was 1/2. What happens at 1/2? It's an intercept actually first, right? It's an x-intercept, like 1/2, 0. Tell me about what happens after 1/2. It is increasing, and it is concave down. So you have to be careful because it doesn't have any maxes or mins, so it continues to increase. Don't draw it such a way that it sort of looks like a parabola. It's not. It continues to increase at a slow rate, right? This is not happening very quickly, but it's still concave down and increasing. Doesn't have to have a max or min for that to happen. Is it good? All right.